So we're going to do one last example for integration by parts. It's something that is kind of called solve for the integral. And we're going to integrate, let's say, 6 sine of x cosine of x dx. Now there's a couple ways you can do this. One of them is to use a trig substitution that I think I emailed you as part of some other stuff. That trig substitution is this one right here. One of the problems in your homework is going to have you work this example several different ways. One of them is integration by parts. One of them is with this trig substitution. There's like, I think 3 or 4 different ways you can do this problem. But the solve for the integral is kind of cool. It just feels like hocus pocus when this works out. So let's solve this by a u substitution, or excuse me, integration by parts. So I need u and dv. Now, with sine and cosine is not much of a difference here. But one thing I would suggest is that you keep the 6 inside the integral. Rather than, if you put it on the outside of the integral, it might make it simpler to an extent, but then you have to distribute to everything when you're all done. So it's up to you what you find most convenient. So I'm going to let u equals 6 sine of x, dv equals cosine of x, dx. There's a convenience to that, and that is when we integrate this, I just get sine of x, and the derivative of this is going to be 6 cosine of x dx. So, all right, sine of x. So let's put this in here, and what do I get? I get u times v, so it's going to be 6 sine squared of x, right, because I have a sine times a sine, minus the integral of v du, which is 6 times sine of x cosine of x again, and then the dx. And if you look at this, it might feel like, gosh, weren't we just there? So let me write it all out in one nice long line so we can take a better look at it. Six sine squared of x minus the integral of 6 sine of x cosine of x dx. And if you're looking at these things saying, hey, those are kind of the same, I can't argue with you. They do look the same. So we're actually going to take advantage of the fact that they are the same and see if we can't pull a little trick to find the antiderivative. And that trick is this. Because these integrals are the same, let's take a look at the coefficients. I've got a 1 of them here and minus 1 of them here. So my trick is I'm going to add this integral to both sides. And I don't really need the equals there. I'm just adding this to both sides. But I want to be clear about something. I'm adding one of these back into my integral. So I'm adding one of them here and one of them here. Why is that important? It's important so that you see what's happening on the left-hand side. Now the easy part is the right-hand side. I just get 6 sine squared of x, and these things cancel, right? That just disappears.
Can you scoot down, please?
And then on the left-hand side, 1 and 1, well, let me pull out my graphing calculator on that one, okay? 1 and 1 is 2. Except I wanted to solve for this expression, the integral of this. not twice that. So what I'll finish up with is I'll divide both sides by 2. So let's put the 2 in there. And then I'll divide both sides by 2. So this by 2 and this by 2. And what's that leave me with? Well, it leaves me with my integral, right? The 2 and the 2 cancel. I'm left with 6 sine of x cosine of x dx equals 3 sine squared of x. And of course, we still have the c. Technically, we had a c up here as well, plus c. You might think, well, wait, c divided by 2, right? Well, a constant divided by 2 is still a constant. And one thing that you might get used to in calculus is that we abuse our constants. These are different constants, even though we label them with the same thing. We just get a little sloppy. Just the way it rolls on that one.
In Weber sign, we just put in everything on the right side, correct?
Yeah, on Weber sign, all you need to do is put in stuff on the right-hand side. Now, you'll see these kinds of problems don't come up when you have things like, so solve for the integral. This one is actually a really nice case. You'll see this kind of stuff come up when you have integral of e to the ax sine of ax or sine of bx, or integral e to the ax cosine of bx dx. These problems lead to the solve for the integral. And I'll put another example like this, like these, into the notes. So it's kind of here. It does get a little bit long. The big thing in working with these things is you've got to take care to distribute your negative signs. And then when you're all done, the way you know you're almost all done is at one point, you're going to get, other than a constant, you're going to get the same integral back that you had to start with. So this expression right here matches this expression right here, except for the constant. So I added 36 of those both expressions. So 36 and 1 gave me 37, and then you divide and solve. So it works out kind of the same. It's just with these, you got to be a little bit more careful with the constants. Okay, like I said, I'll put that one in the notes.
I'm confused a bit about the setup of this one. Did it start off as just a solve by parts, and then you just set that equal to the original integral?
So it was a solve by parts, so it was integration by parts, and after one iteration by parts, one integration by parts, I ended up with this. So this is my integral. This is my u times v minus my integral of v du. And if you notice, on the left and right-hand sides, you have the same integral. This and this are the same.
Right.
So at that point, that's when you can solve for the integral. And what I did is I moved this to the left-hand side. So I took minus one of them here, added over there. That gave me 2 of them on the left-hand side, none left on the right-hand side. Just divide by 2 to finish solving. And that was it right there. So
okay, thank you.
When you, generally speaking, like in the example I was just talking about, what you'll have to do is do the integration by parts twice. And then you're going to get down to a point where you've got that coefficient there is different than the coefficient on the left-hand side, and then you can add and solve. And just keep track of those parts in between. So, but for the ones you're going to see in homework, you're going to have to do the integration by parts twice before you get down to here. Beautiful, beautiful. Okay, that's it for section 7.1. Hope you enjoyed it. We're going to move on to section 7.2. And I think I sent you out a copy of this kind of stuff right here. Some trig identities, just to remind you of. So I know that not everyone's fresh out of trig. So these are all coming from the Pythagorean Theorem. Of course, the Pythagorean Theorem is sine squared of x plus cosine squared of x equals 1. That's the Mac Daddy of them all. And everything from here gets derived from here. You move the sine or the cosine terms to the other side, you get some nice expressions for sine squared or cosine squared. If you divide this by cosine squared, I get this identity. Divide everything by cosine squared, I get a different identity. All right. Actually, I would get 1 plus, no, I get, if I divide by sine squared, then I get 1 plus cotangent squared equals cosecant squared. I didn't write those here. Your half angle identities are helpful in working with your sine squared and cosine squared terms. Sometimes I call these power reduction formulas because it helps you go from a sine squared term down to a cosine term. Something from the second power to the first power. And that quite often is very helpful. Your double angle formulas, the problem we just finished, an alternative to what we did was to use the double angle formula. So you could have just done that and you would have been in good shape real quick. You replace sine of x, cosine x by 1/2 sine of 2x. The big thing in this section is to kind of think ahead because we're going to make a lot of u substitutions. So if u is equal to tangent, the du term should have a secant squared. If u is equal to secant, du should have a secant tangent. And if u is equal to sine, du should have a cosine, and vice versa. If u equals cosine, du should have a sine. So you want to think ahead to some of your substitutions. So let's do some problems. We'll start with one from the book. Integral of sine squared of x cosine cubed of x dx. Okay. So problem here is that, you know I've got derivative of sine is cosine, derivative of cosine is minus sine. It doesn't look like there's a nice easy substitution setup. So I'm going to take a note. I'm going to take note of the fact that I have got an odd value for cosine. And let's keep in mind that I can rewrite this as sine squared of x times cosine squared of x times cosine of x dx. And what I'm doing is I'm anticipating an eventual u substitution. So cosine of x dx, I took that extra, because I had an odd term here, I took that extra cosine and I'm leaving it off there to be part of my du substitution. This, by the way, is section 7.2. Probably should have mentioned that. So let's write it up here, section 7.2.
Was the last problem we did part of the same section?
No, the last problem we did was still section 7.1.
Okay.
Although you could do it with methods from this section as well. In fact, one of the homework problems from this section is just what we did with the last one. So those of you who are paying attention, taking good notes, hey, I've already solved one of your homework problems for you. Let's look back at our little substitution guide. Cosine of x dx is the du term for this kind of a substitution, if I had u equals sine of x. But right now, this problem has sines and cosines. So what I'm going to do is I'm going to get rid of the cosines this way. Sine squared of x, 1 minus sine squared of x, cosine of x dx. So, okay, nice. So I got rid of my cosine squared terms. The only thing I got left is like a du term. And now I'm getting a little bit closer to substituting. If that's going to be my du term, what was u equal to? What's the u for this du term?
Sine x?
Yeah, sine of x.
Sine of x, yeah.
Yeah, sine of x. Let's watch what happens. This is going to become the integral of u squared times 1 minus u squared du. That's not so bad. To solve this one, I'm going to distribute u squared minus u to the 4th du. And I hope that that's not too much of a problem to integrate. That's going to be u cubed over 3 minus u to the 5th over 5 plus my constant. Now, I didn't try and solve a problem in u. I was trying to solve a problem in x. So let's put that back in here. And that would become sine of x cubed. So sine cubed of x over 3 minus sine to the 5th of x over 5 plus my constant. Yay.
I'm a little bit confused. Can you just run through like all the steps, like an overhead kind of?
Sure, absolutely. Yeah. So in looking at this, I start thinking about u substitutions. And I realize that, you know what? If I'm going to do u equals sine of x or u equals cosine of x, then my du term is going to either have a sine or a cosine. But because I've got an odd number of cosine terms here, then I can split one off. I wrote that as cosine squared times cosine. So I still have 3 cosines here, right?
Right.
Okay. But one of them is split off. And this is becoming my du term. I'm setting up my du term. Okay. If that's the du, that du goes along with u equals sine of x. So, okay, u equals sine of x. And what I did next is I used the Pythagorean Theorem to help me out here. That way I turned everything into a sine. I wanted everything in terms of sines, that way I could get rid of the sines. I could integrate with that stuff. So, let me see here. Green, blue, green. Yeah, I guess we'll use this one. No, that doesn't work too good. Yeah. So I went from here to here using the Pythagorean Theorem. The reason I did that is because now I got the rest of my function, other than my du term, I got the rest of the function in terms of sines. So now I can make my substitution. U equals sine of x, so that's sine squared times 1 minus sine squared, or u squared times 1 minus u. Integrate, substitute back for u.
So basically we have to recognize like the trig identities.
Yeah, pretty much. Now, I did email you this sheet. These are all the things that you're going to need to have handy when you're doing these types of problems. You've got some basic trig identities. couple half angle identities. In fact, we'll use the half angle identity next. And then your double angle formula. Okay. Oh, and then this is just thinking about your u terms and your du terms. If this was u, oh, your du should have a secant squared. U, du, etc. Let's do a different one. And actually one with some numbers. Let's take a look at, let's see, do I have it graphed up here? Yes. So we're taking a look at this function. So this is section 7.2. And if you like, I'll put this link in the chat, help you out. Okay. So there's that link if you want. We're going to rotate this around the x-axis. So the function that I'm working with is really an area bound between y equals 6 sine of x, and that's going to be also bounded by the x-axis. Y equals 0. And then, what was the interval? I'm sorry, I need to switch back here for a second. Pi over 2 to pi. There we go. X equals pi over 2, x equals pi. And we're going to rotate this around the x-axis. So y equals 0. Okay. There's our problem. All right, well, let's take a look at this. And if we're going to rotate this around the x-axis and solve this with the disk method, what kind of a slice am I going to be taking into my region? What would that slice look like?
dx.
The dx slice, perfect. So it would look kind of like this, a little dx slice. And when you rotate that around our region, that's going to give you a disk. How come it's not giving you a washer? It's not giving you a washer because our region is flush with the axis of rotation. So that pink region sits completely tight with the x-axis. So, okay, let's find a volume of one disk. So the volume of one disk is going to be volume is area times the thickness, so pi r squared times the thickness, which is going to be dx. The radius is going to be top minus bottom. The top of the function is going to be 6 sine of x. Bottom is going to be 0. So I'll end up with pi times 6 sine of x squared dx. So the nice thing about this problem is that it's also a review of some of the work you did in section 6.2. So it gives me 36 pi sine squared of x dx. And now to try and find the value of this thing, or excuse me, trying to find the volume of this thing, I've got to integrate. I'll take the 36 pi out in front, sine squared of x dx. Well, what about our limits of integration? Our limits of integration are going to be from here, pi over 2 to pi. That's where you can take the slice in this figure. So let me see if I can put, there we go. So a little more clear. From pi over 2 to pi, and pi over 2 to pi, like that. So this is what makes this a problem relevant to this section, is that you got a sine squared term. Now with your even sine terms, or even cosine terms, it's difficult to try and integrate these things. So that's why we have our power reduction formulas. The good news is that you can have this sheet handy on your test. If you're taking this in a normal semester, you'd have to have it memorized, but it's not a normal semester. So sine squared can be replaced by 1/2 times 1 minus cosine of 2x. Basically, when you're going from a squared down to this, you have to double the angle. So if I had a 3x here, this would be a 6x here. So let's take a look. That's going to be 36 pi times the integral from pi over 2 to pi of 1/2 1 minus cosine of 2x dx. And the 1/2 and the 36 will cancel. So I'll bring that out and I'll have 18 pi times integral from pi over 2 to pi of 1 minus cosine of 2x dx.
Why do you have to change it from sine squared to that 1/2 1 minus cosine 2x?
Great question. It's because I don't have an antiderivative for this. I can find an antiderivative if I don't have something to a power. But here, I'm like, I don't have an antiderivative. By the way, when you do problems like this for me, no one should be just jumping from here to an antiderivative. There's a lot of work that I would expect to see in between there. So if you're making that kind of jump, you're making me nervous, and that's being polite. So please, I would want to see some work here, and that work is to replace a sine squared or a cosine squared term with something like this. Now, if this was sine to the 4th, what I would do is I would write that as, I'd write it as sine to the 4th of x. I'd write it as sine squared squared, and then use the power reduction formula in here, and then square out the result. Maybe I can do like one like that next time. Okay, 18 times pi over 2 to pi. Antiderivative of that's going to be x minus, is anyone getting better at doing these in their head? What's going to be the antiderivative here? Well, instead of multiplying by 2, I need to divide by 2, which is multiplying by 1/2. Sine of 2x. Now we got to go back and take a look. Do we have the right sign here? Would the sign have changed? Well, when I differentiate sine, what do I get? Derivative of sine is a cosine. So the negative term is appropriate out here. In other words, it's not going to change. I don't have to put a plus here. Okay, let's keep going. 18 pi, plugging in the pi, minus 1/2 of sine of 2 pi, sine of 2 pi. So that's my upper limit. And then I need to do the lower limit. So it's going to be pi over 2 minus 1/2 sine of 2 times pi over 2 is just going to be pi. And something nice happens. That term is 0. That term is 0. Sine of pi and sine of 2 pi, the y coordinate at both of those points is 0. So I'm left with pi minus pi over 2. Pi minus pi over 2. That's going to be pi over 2. Pi over 2. The 2's cancel. I'm left with 9 pi squared. Okay. Well, I think we got to stop here. I will take some questions on this one, though.
What did you do from that pink move to the black one underneath it?
Oh, I just took the 1/2 out. 1/2 times 36 is 18. That's all I did. Yeah. Appreciate it, though. It's got to be something else. I know it's like late, you're tired. So, nothing else? Okay, let's stop.